Hi, my name is Dr. Ken Tyndall and I am the CTO of Canis Labs. In this video I'm going to talk about getting started with CryptoCAN using our micropython firmware for the CANPico board. But first I want to give a quick overview of CryptoCAN. What is CryptoCAN? It's an encryption system for CAN bus messages and is designed to fit with the publish-subscribe model of how CAN communication works. It takes in any plain text CAN frame and encodes it into two 8-byte ciphertext frames. These frames contain details of the original CAN frame and a message authentication code or MAC. These ciphertext frames are transmitted as a pair on the CAN bus, and then as they arrive at a receiver, they're fed into the decoder and turned back into the plain text CAN frame. The decoder also checks the MAC to see if the message has been tampered with or is a forged message. This prevents the most common attack on CAN bus, the spoof attack, where a device on the bus sends messages that pretend to be from another device. The messages are also secret. This is useful because it makes it much harder for an attacker to reverse engineer the messaging on a CAN bus. Let's have a look at the CryptoCAN messaging stack. At the base is a layer of cryptographic primitives. The primitives CryptoCAN uses are the standard NIST AES and CMAC algorithms, plus random number generation and key storage functions. These are all provided by the SHE hardware security module standard. CryptoCAN is based on these primitives for portability, because they can be implemented in hardware or software, and CryptoCAN defines a standard API to this layer. On top of that is the CAN messaging scheme. This is what deals with encoding plain text to ciphertext CAN frames and decoding them back again. On top of the two layers is the application software. This normally accesses just the messaging API, but sometimes will access the key setting part of the cryptographic API. Canis Labs uses the Raspberry Pi Pico with the CANPico board as a platform for evaluation and rapid prototyping. We already produce micropython firmware for this hardware to give Python access to sophisticated CAN functions, and our latest micropython firmware adds CryptoCAN support. The micropython firmware contains the standard C distribution of CryptoCAN that includes a pure software emulation of an SHE hardware security module. Underneath the standard C software-only stack is an API to non-volatile memory for key storage, and here there is a driver for the Raspberry Pi Pico's flash chip. On top of the C API for the cryptographic layer is C code that wraps up the API and makes it available to Python programmers with a class called HSM. On top of the messaging API is C code that wraps up this API and makes it available as a class called CryptoCAN. Along with the existing CAN APIs in Python, an application coded in Python can now send secure CAN messages with CryptoCAN. So let's get started with CryptoCAN in Python. We start by provisioning the HSM. We only need to do this once because everything is stored in Flash and will be retained across power cycles. We provision it by providing a secret key, which causes the software to initialize structures in Flash, erasing any old structure. Only if the Flash gets corrupted or erased will reprovisioning be needed. Now remember, this is a software emulation of an SHE hardware security module. The Raspberry Pi Pico doesn't come with a real one. A real one wouldn't let us do these things. It would come from the chip factory pre-provisioned and wouldn't let us do a factory reset on it. And if we forgot the keys on it, then the chip becomes a brick. Once we've initialized the HSM, we can provision it with some application keys. CryptoCAN uses a pair, one to encrypt and decrypt the message, and one to generate and verify the message authentication code. The SHE specification defines ways to securely program keys into the HSM, but this is quite complicated and requires a key database and programming tool to generate the key setting data. So to keep things simple while we're learning and experimenting with CryptoCAN, a backdoor API has been added to let keys be programmed straight in. But remember that this should not be used beyond early learning stages and will anyway be removed from the API in the future. So we have a couple of CANPico boards here. These are the Raspberry Pi Picos, and these are the CAN controller and transceiver on the CANPico board. They're connected via USB, USB serial, so we'll be logging into these boards over terminal emulators. This is the debug CAN high-low pins, and we just use that to connect the CAN buses together instead of using the normal screw terminals. And each end of the bus is terminated with a terminating resistor jumper. Okay, so this is a standard Linux Ubuntu install, and the first thing we want to do for provisioning hardware security modules is to get some keys. and we're just going to use the built-in Linux support for generating random numbers. So that's a pair of keys we'll use for the secret keys for each hardware security module, and then we'll create another pair of keys for encryption and authentication with CryptoCAN. So let's go and log in to the first board. Bring up Wrapup, and we'll bring in all of the micropython Pico firmware modules we need from Python, and we'll also bring in unhexlify. Oops. And that will turn the hex keys we've just created into bytes, which will be set through the API. So what we're going to do is create the hardware security module, and by giving it a secret key value, like so. Oops, I'll go back to our keys. So we're going to create this will be our secret key, and we create that secret key into bytes and then set it into the hardware security module. And we could try typing hexlify correctly. Right, so that has created a factory reset hardware security module. And now we need to create some embedded keys. So let's get that spelled correctly. So the encryption key, we'll create a key value here. It's that, and the authentication key we will set to be that. Like so. And now we've got a hardware security module that's been set up. We can use our special development only backdoor API call to set the keys, and the key we want to set. So we will set key 1 to the encryption key, and the key value is EK. And we will set key 2 to the authentication key, and we need to tell it that it's an authentication key. So it defaults to an encryption key, but we need to set its key permission to say authentication key. So now we've created or provisioned the hardware security module with key 1 and key 2. So if we now go across and log into the second CANPico board, and do the same thing. Like so, and we will create our secret key from this one here. So these the secret key inside the hardware security module is the top level key that is able to authenticate lower level master keys, and it also sets up the random number generator. So that's factory reset our hardware security module now, and now we need to basically set in the same keys that we did before, because we're going to share these key pairs between the two ends. So that's our embedded encryption key, and this is our authentication key. So these are the same values we're using at both ends, and we will set key 1 to be the encryption key of the pair, and we will set key 2 to be the authentication key and set its permission to be used for authentication. Right, so that's both ends now provisioned. We close that. We now don't know what the keys are. They've just been set up. So, for example, we could use the random number generator. So this is a full security module, even though it's implemented in just software. And that's the two ends provisioned with the same keys. So now we're in a position to set up CryptoCAN to communicate securely over CAN bus between a sender and a subscriber. And we can come back and do that in a moment. Now that we have a provisioned HSM on both boards, with the same keys programmed into slots 1 and 2, we can get started with encrypted CAN messages. First, we boot up the HSM to initialize the random number generator, load its keys up, and so on. Then we create a CryptoCAN context for a source of CAN messages. This context specifies the key numbers and the B flag. The B flag is a bit within the CAN ID that will be 0 for frame A, the first frame of the pair, and 1 for frame B. We create a context on the receiver with the same keys and B flag. Once we've created the context, we can start pushing plaintext CAN frames through it to get pairs of ciphertext frames, and then transmit them on the CAN bus. Then at the receiver, we run the ciphertext frames through the CryptoCAN context and get back to the plaintext CAN frame. Let's go to the lab and try it out. Let's have a look at CryptoCAN with the MicroPython API in practice. So let's open up a terminal connection to sender board and another one to the receiver board. And let's bring in all the MicroPython packages we need. So on the sender, let's fire up the hardware security module and fire up the CAN controller using the standard CAN API. And then on the receiver, we'll do the same. So we've already provisioned the hardware security module with our keys that we're going to use for CryptoCAN. So that's all fired up. Now let's create a plaintext CAN frame. So that's ASCII for hello, that's our plaintext CAN frame, and we can just test the CAN controller is working. And that's returned the CAN frame as we expect. So now let's use CryptoCAN by creating a CryptoCAN context for the transmit side. And all receivers would do the same on the receive side. We're using all the defaults here, so the key pair is 1 and 2, which is why we programmed the key pair 1 and 2 of in the hardware security module earlier. And the B flag is set to bit 0 of the CAN ID is our default zone. So let's create some CAN frames from our plaintext frame. So these are the ciphertext frame A and B. That's an 8-byte frame, and an 8-byte frame, and the CAN ID is 100 for frame A and 101 for frame B. So the bottom bit's been set for the B flag. And we can send frames using the Send Frames API over the CAN bus. And on the receive side, we can pick them up. And we have picked these up, so that's our ciphertext that's come across. And then once we've picked them up, we push the frames through. So push frame A and B in that order. Now that's not received anything because with CryptoCAN, the very first message after the CryptoCAN context on the receiver is initialized is always dropped because it doesn't have sufficient context of previous ciphertext values. But if we create some more frames, so this is the same plaintext payload, same plaintext CAN frame, but now the ciphertext is changed from before, and we can send those frames. and they've gone over to CAN bus, and we'll pick them up. And they're the new ones. And we will push that through the receive context as we did before. So it's the first frame and the second frame. And now we have decoded the plaintext CAN frame back again. And that's its payload. And that's its payload. So that's CryptoCAN working. We could just check that by creating a different CAN frame. Same as the same ID. But now the payload has changed to hello world, and we create those frames from that new frame as before, and we send those frames on the CAN bus, and we pick those frames up and we push them into the context, and there we go. So that's the plaintext CAN frame recovered as normal. So that's basically how CryptoCAN works. Just for a bit of fun, we could show how CryptoCAN is in fact an end-to-end encryption system. So if we create a third CAN frame, plaintext CAN frame, like so, and we create the ciphertext for that. Now, if we bring in our now what we can actually do is create our own CAN frame, not via CAN bus, but by extracting the information that we know. So the first ciphertext frame has a payload of this, and we can convert it. So effectively we're using copy and paste between terminals as out-of-band communication. So we could have put these CAN frames and encapsulated them into some other transport mechanism, such as TCP/IP over Wi-Fi or an Ethernet frame or something like that. But here we're doing it manually just to prove a point. So here we paste it. So this has not gone via CAN, of course. So we've created these CAN frames, and if we push them through frame A, frame B, and there, that was our plaintext CAN frame, and we've recovered the same plaintext CAN frame here. But the messages this time didn't go via CAN, so we could use CryptoCAN as a mechanism for bridging between CAN buses over some other link, like Wi-Fi or Ethernet. So that's CryptoCAN. Let's finish up this getting started video with a wrap-up of where we've been. So that's how to get started with CryptoCAN. We provision the HSM with keys, create a context for each source of CAN frames, encode the plaintext CAN frames, send them as ciphertext frames, and then decode them back into plaintext frames. That's the basics of CryptoCAN. There are more advanced features of CryptoCAN. One feature is for protecting messages against replay attacks. A replay attack is where the attacker stores previously seen messages and then sends them again later to get receivers to act on them. CryptoCAN supports a freshness value that indicates when a message was created so that receivers can discard stale messages. There is also support for debugging. For example, the encryption can be turned off, leaving the message authentication code. The payload of the plaintext CAN frame is in frame B, and existing CAN tools decode that in the normal way during development, with the encryption switched back on for deployment. And as we discussed earlier, there is a proper way to securely set keys through the HSM instead of the simple backdoor mechanism we used in this quick start guide. To learn more about CryptoCAN, download the Canis Labs white paper or the National Defence Industry Association GVSET's 22 conference paper called Defending CAN Bus that describes CryptoCAN in detail. And you can get more information, including the MicroPython firmware for the CANPico, from our website at canislabs.com/CryptoCAN. Thank you for watching.